We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system.
We're looking at Neptune's orbit, and it's not following Newton's laws. And this is odd.
When Neil deGrasse Tyson made his astonishing announcement about Neptune, it didn't just catch the scientific world off guard. It rattled the very foundation of how we've modeled planetary behavior for decades. Known for his ability to make even the most abstract astrophysics sound thrilling, Tyson stood before an international audience and delivered a revelation few were prepared for. Neptune, the icy distant outlier at the edge of our solar system, isn't just peculiar. It's actively rewriting the rules we thought governed planetary systems. From a moon orbiting in reverse to its ability to emit heat far beyond what it receives, from winds that howl faster than the speed of sound to violent storms that may rain actual diamonds. Neptune defies logic at nearly every level. None of these phenomena fit neatly into the long-standing models of planetary interiors or magnetospheres. The planet we once thought of as quiet and remote may be one of the most chaotic and complex bodies in the solar system. To grasp the weight of what Tyson revealed, we have to rewind almost 200 years. Neptune wasn't found by accident. In the early 19th century, astronomers studying Uranus noticed its orbit was ever so slightly off, drifting inexplicably as though something unseen was tugging at it. French astronomer Urbain Le Verrier crunched the numbers and predicted the location of the invisible culprit. In 1846, German astronomer Johann Galle pointed his telescope to the exact coordinates Le Verrier had calculated. And there it was, Neptune, our solar system's 8th planet, an enigmatic blue sphere orbiting in the frozen reaches far from the sun's warmth. For over a century, Neptune remained little more than a mysterious dot, until 1989, when Voyager 2 flew by and offered our first real glimpse. What it saw was a planet alive with activity, roaring supersonic winds, transient storms, faint ring arcs, and a striking deep azure hue caused by trace methane in its upper atmosphere. Voyager discovered the now famous Great Dark Spot, a massive Earth-sized storm and a smaller sibling storm farther south. But only a few years later, those storms had completely disappeared when the Hubble Space Telescope checked back in. Unlike Jupiter's long-lived Great Red Spot, Neptune's weather systems come and go in rapid bursts, adding to the planet's air of mystery. Despite that dramatic introduction, Neptune remained poorly understood. That is, until Tyson's dramatic disclosure, based on newly synthesized data from the James Webb Space Telescope and cutting-edge Earth-based radio arrays. The findings revealed anomalies, deep inconsistencies in how Neptune behaves internally that current planetary models can't explain. Tyson explained that Neptune's interior isn't structured in neat, orderly layers like we once thought. Instead, it's marked by chaotic convection, movements of material that challenge our assumptions about how heat and pressure should behave in such a distant world. Despite an average temperature of 201 degrees Celsius, Neptune gives off more than twice the energy it gets from the Sun. Uranus, its near twin in size and composition, radiates almost nothing. At Neptune's distance, the Sun is 900 times dimmer than on Earth. So where is all that energy coming from? The standard explanation has been residual heat from its formation. But Tyson offered a new theory. Exotic chemistry deep inside Neptune's mantle may be generating that heat. At such extreme pressures and temperatures, normal materials behave in exotic, barely understood ways. One such material is supersonic ice, a strange hybrid phase of water where hydrogen ions move freely through a rigid oxygen lattice. Neither fully solid nor liquid, this material conducts electricity and may exist in vast, swirling layers inside Neptune, converting mechanical pressure into thermal energy, essentially powering the planet from within. This may also explain Neptune's extreme winds, the fastest in the entire solar system, clocking in at over 2,100 kilometers per hour, easily surpassing the speed of sound. On Earth, wind and weather are driven by solar energy. But on Neptune, where the sun is little more than a bright star, another energy source must be at work. Tyson proposed that these gale-force winds may be driven from below by rising waves of internal heat and pressure changes, forming storms not because of sunlight, but in spite of its absence. And then there's the planet's magnetic field, perhaps the most confounding of all. Unlike Earth's relatively stable, centered field generated by its spinning iron core, Neptune's magnetic field is tilted 47 degrees from its axis and doesn't even pass through the planet's center. What's more, it fluctuates wildly. New observations show the field's strength and structure shift over time. Sections pulse, drift, and vanish in rhythmic cycles. Tyson introduced a radical theory. Neptune's magnetic field may not originate in the core at all, but within the mantle. That's an unprecedented idea. But if the mantle contains conductive supersonic ice and other exotic materials, and these substances are in motion, they could generate a magnetic field that behaves in unpredictable ways. The field's drift, asymmetry, and instability might all stem from these moving layers of conductive material far above the core. Then came the jaw-dropper. Tyson proposed that Neptune's interior may not be homogeneous at all. Instead, it could be riddled with stratified regions and massive cavities, what he called resonant chambers. These irregular structures could trap and focus energy, generating turbulence and strange, low-frequency radio emissions, the kind now being picked up by sensitive instruments. These radio waves don't match auroral patterns or solar wind interactions. They seem to come from deep inside Neptune, and some researchers think they may point to quantum-level phenomena playing out on a planetary scale. The takeaway? Neptune is not the dormant, icy world we once imagined. It's a living, dynamic system, potentially operating by principles we don't yet fully understand. And yes, as wild as it sounds, Neptune likely experiences diamond rain. Under the immense pressures deep within the planet, methane molecules are crushed. Their hydrogen atoms are stripped away, leaving pure carbon, which forms diamonds that may literally fall like hail. Some theorists suggest vast diamond oceans, where chunks of solid carbon drift in a sea of liquid carbon. Recent lab experiments have demonstrated that such phase changes are physically possible. Even Neptune's largest moon, Triton, adds to the planet's strangeness. Orbiting in the opposite direction from Neptune's spin, a clear sign it was captured, Triton is likely a wayward dwarf planet. Its arrival may have destabilized Neptune's original moon system, leading to collisions that created its current dark ring arcs. Voyager 2 observed active geysers on Triton's surface, evidence of internal heat, possibly driven by tidal forces or a concealed ocean beneath its crust. Everything around Neptune, it seems, pulses with change and energy. So, is NASA hiding something? Not exactly. Without the power of tools like the James Webb Space Telescope and recent upgrades to ground-based interferometers, we simply didn't have the resolution to see what's really going on. Tyson's core message was clear. The more precisely we look, the more radically the universe begins to reveal itself. Neptune may not just be a planet. It could be something entirely new. A bridge between planets and brown dwarfs, an object that generates its own energy, its own weather, and a wholly unique magnetic field. And if Neptune is this different from what we expected, what else are we still missing? Let us know in the comments. Which planet do you think is still hiding secrets? And if this changed how you think about Neptune or space science, make sure to hit that subscribe button and ring the bell. Because if this is what we're just now discovering about Neptune, imagine what's next.